This conference will now be recorded.
Wonderful. So today we have an exciting talk. Please make sure you mute your microphone during the presentation. We'll have a presentation first, then followed by a question session. You can either write down the questions like in the chat, or you can ask the questions like when we are in the question session. So it's an honor to introduce Professor Balaji from the Computer Science and Electrical Engineering Department of Stanford University. His research interests are in computer networks, notably data centers and cloud computing. From 2008 to 2016, he worked on a societal networks vital for society's functioning, such as transportation, electricity, and recycling systems. He led the development and deployment of nudge engines for transportation systems, notably used in Singapore Mass Transit and the Bay Area Rapid Transit, known as BART, wellness programs, and corporate learning programs. Based on his work, he co-founded Urban Engines, a startup which has been acquired by Google in 2016. Professor Balaji and Mendel Rosenblum have led the self-programming network research group at the Stanford University since 2016. Using a purely edge or NIC-centric architecture for sensing, inference, and control, their goal is to make data centers and cloud computing infrastructure autonomous and interactive. This has led to the development of a software-based system called Huygens for highly accurate network clock synchronization. Pursuing the exciting consequences of an accurate time source for distributed systems and networks, they have developed a multi-leader version of the Raft consensus protocol called CRAFT, an event ordering service for permissioned distributed ledgers called Clockchain, a novel way of controlling network congestion without using network support called on-ramp, and a fair financial exchange in the public cloud called CloudX. Professor Balaji has received the NSF Career Award, the Erlang Prize from Inform's Applied Probability Society, the Rollo Davidson Prize from University of Cambridge, and delivered the Lutheran Lecture of the Dutch Operations Research Society. Professor Balaji is an IEEE Fellow, the ACM, and Alfred Pritchard Sloan Foundation. He has received the inaugural IEEE Innovation in Societal Infrastructure Award for his work on societal networks and the IEEE Koji Kobayashi Award for his work on computer communication. Today's talk is about Huygens, a software-based system for accurate and scalable clock synchronization and its consequences. Without further ado, Professor Balaji, the floor is yours.
Thank you, Ahmed. I thought normally the bio is just read and not read out. So, but thank you for the generous introduction. Appreciate the invitation to speak here. I want to share with you some work we're doing at Stanford that started with the overall theme of self-programming networks. As Ahmed's already said, 5 years ago, Mendel Rosenblum, my colleague, and I started working with some students and industry collaborators to make networks autonomous and interactive. And thank you and a shout out to our sponsors, many of whom are tech companies based in the Valley, and the middle row is financial companies who are amongst the key industry folks that care about accurate clocks. That's sort of basic to the way they operate. I'll tell you a little bit about it. So, but thank you to our sponsors. So as soon as we got down this self-programming networks path, and given that we've taken an edge-based approach, it became important for us to have an accurate clock sync system across all the nodes. Whether we wanted to use this for real-time measurement or control, this became important straight away. And that led us to thinking of clock sync. But we know, just, given how hard it has been to do even just NTP accurately, if you want to do it down in the nanoseconds, we know it's a pretty hard problem. But we had a solution that helped in this regard. But before getting there, just the way distributed systems and packet switch networks have evolved, we've always had to worry about time. In fact, going from centralized to distributed computing or circuit switching to packet switching, we gave up time, and in exchange, we wanted scalability, right? And so, whether you look at textbooks, or this is Leslie Lamport's paper, seminal paper on clocks and event ordering, or if you look at just stories from industry, you have the sense that don't trust time, and time is not easy to synchronize. And so we've sort of designed and worked around, systems that have we've evolved systems and protocols that are clockless, right? Because accurate time has not been easy to get. But when we started looking at self-programming networks, we came up with a solution called the Huygens algorithm, which I'll present. It's been published. My co-authors are named over there. And there was a New York Times story on our work with NASDAQ. This is the financial exchange problem where clocks are very important. I hope I'll have time to get around to this at the end of the talk, because this is one of the key motivating applications. Okay. So at a high level, what was the main point of departure? What did we do that was different that got us down this path of our solution? So if you look at clock sync, accurate clock sync, historically, it's always been the case that people have wanted to use the network itself to communicate time across the network from host to host. So if you have some number of servers connected to each other through a layer 2 or a layer 3 network, then we wanted to use the network elements, so synchronize the switches and things in between, and then communicate time from one side to the other. This has been sort of the ethos, and there's a number of algorithms which are listed here. PTP, this is IEEE's 1588 protocol, the data center time protocol from Cornell, DPTP from, I think, NUS, and then pulse per second. There are a whole bunch of folks who've been looking at this. And the key aspect here is that the network elements need to participate, either actively or in what's called a transparent mode. So our point of view was a departure from this, and we took time as a service and unhinged it from the hardware and attached it to the apps. So we think of time as in the service of applications, and each app can get its own time synchronization system, and so you don't have to synchronize the nodes in the network. And taking that point of view is only really possible because of advances in ML. So in other words, if we weren't to be able to use some of the techniques that have been developed in ML, let's say certainly in this century, and maybe a little bit in the last part of the previous century, I don't think the solution is feasible. Okay, so that's the key change that allowed us to do this. But if you could do this, then of course you could scale in size and distance, as I'll demonstrate to you. And you can run it on just public cloud as well, where you certainly don't have access to network switches. Okay. So the moment we got accurate clocks, our research program at Stanford somewhat oriented around this theme. So our sensing, inferring, and everything became around the fact that there are accurate clocks available. And so on the bottom part of this diagram in blue, we were applying accurate clocks to things like network telemetry or congestion control from the edge. And I have a few things to say about that in the presentation. On the top, we began to look at a number of different distributed systems that had all been developed without the need for accurate clocks. And we began to see what would happen if they had accurate clocks, like distributed databases and consistency, or event ordering in ledgers, consensus protocols like Raft and Paxos, and so on. Okay. And finally, we developed also an application ourselves, which is trying to see if we can build a financial exchange in the cloud. Okay. So if you have questions, feel free to ask as they come up, because there's a variety of different things I'll be covering in this presentation. And so so this is the introduction. What I plan to do is to tell you about the clock sync algorithm. What is it? How does it work? How does ML play a role? And a little bit about the telemetry control and CloudX. Okay. So the setup here is that there are n clocks that are connected by some packet switch network, where one of the clocks is a reference clock, and we want to synchronize the other n-1 guys to that accurate reference clock as accurately as possible. That's the problem. And so in order to do this, we introduce what we call a probe mesh. Each clock randomly picks a constant number that is not constant, meaning not depending on n, in, say, for example, 5, other clocks, and they'll exchange probes. So each clock probes 5 other clocks chosen at random, and then they exchange probes. And the probes are ACT. Okay. And the timestamps carried in the probes and the ACTs allow these clocks to synchronize according to the algorithm that I'm going to describe now. Okay. So whether you have 100 nodes or 100,000 nodes, each node is only probing 5 other nodes. So the per node work is always a constant. Okay. And the way you should think of this is there's, each node is running an agent, and these agents are doing the probing and the processing of data locally, and then is eventually combined, in a global step. Okay. And the algorithm will describe that in detail. So let's just take one pair of clocks, let's say A and B, and let's say that the actual time is T, but the clocks A and B are off from the actual time by some unknown deltas. And so A sends a probe to B and takes a timestamp at the transmit side, and B gets a timestamp on the receive side. And here the timestamps can be at the network interface cards, which give you the most accurate sync, or it could be the host clocks, the CPU clocks, which you get just by a syscall, and then, or it could be just so from the kernel or from the user space. So you could have timestamps, or if you're working within a virtualized environment, it's the VM's clock. Okay, and so a probe goes in one direction, an ACK goes back in the other direction. So you get 4 timestamps for every probe ACK pair. And if you start looking at processing this, so pretty much every algorithm does what I'm about to say, and the difference comes later. So the equation that receive time is always equal to transmit time plus delays is unconditionally true, right? So if you take the faulty receive timestamp and correct it, which you don't know what the correction is, but mathematically you can write it down. This is the correct receive time equals the correct transmit time plus propagation and queuing delays. Okay, and so if you arrange for the unknowns to be on one side, then and then also remove this negative quantity, you get an upper bound. So you get that this unknown clock difference between A and B is upper bounded by these timestamps, the difference in these timestamps. And similarly, you get a lower bound on the same quantity using the ACK timestamp. So using the 4 timestamps, you get an upper bound and a lower bound. So if you picture these bounds, this is what they look like. This is from the Google's 40G testbed that we were able to work with. So here, as you can see, as you can see, the time plotted on the x-axis is time as seen by clock A. This is time equals 0 seconds and time equals 2 seconds. Each blue dot is an upper bound on the discrepancy, which is what is plotted on the y-axis. The delta between the 2 clocks is plotted on the y-axis, and each blue dot is an upper bound, and each green dot is a lower bound. Now, the thick blue line is all the probes that made it in the shortest time. So it's the least upper bound. And similarly, this is all the guys that went in the reverse direction without delays. So it's the greatest lower bound. This is the green line. All these guys out here and up there got delayed. So these faulty timestamps cause these spurious points in between. These are not actual data points, but the way the NIC timestamps the packets, we have to deal with them as bad data, and they affect the performance, as you'll see. Okay. So is this clear? Is this so? You have two clocks, the exchange probes, and if you plot, these bounds, these values, receive timestamp minus transmit timestamp in one direction, and transmit minus receive in the other direction, you get these bounds. Okay.
Is
So
this
now,
similar?
yeah, go ahead.
This is Datan from NVIDIA, Professor Balaji. My question is this concept similar to the concept of lucky packet?
Sorry, is this a concept similar to the concept of?
Lucky packet. It's a paper published a decade ago about relating only to the sampling that stole the minimum latency.
Yeah.
And by
So I don't know that paper, but I agree with you. The idea is related because you're looking for these blue lucky packets that sit on that thick line, and the lucky packets in the reverse direction on the green thick line are what you're looking for. Okay. But you don't know automatically whether a packet was lucky or not. It is kind of estimated empirically, right?
right.
But I'll show you a method where you can tell if the packet was lucky or not. Okay. But that's the idea. But if you have these data, then assuming that the time taken to go from A to B is nearly equal, or let's say exactly equal to the time taken to go from B to A, then you're looking for this middle red line. If you get this middle red line, then you know how to synchronize the clocks. Specifically, it says that when the time at clock A is 0, the time at clock B is minus 93.3 microseconds. And similarly, when the time at clock A is 2 seconds, the time at clock B is 2 minus 96.6 microseconds. So clock B is ticking slower than clock A by 1.65 microseconds per second. So it's gradually falling behind relative to clock A. Okay, that's what this data is telling us. So if we could work this middle red line out, you'd sort of solve the problem of clock sync. And pretty much, whether it's PTP or other algorithms, try and do the same thing. Okay. And so, but there are problems that complicate this. The clock drifts are not linear. In other words, it's not the case that clock B's frequency is always lower by exactly this amount. If you look at longer time intervals, then it could fall, the frequency can change and it could fall behind faster and faster. And this is because of temperature variations and other effects like, vibration, noise, and stuff. So the way we synchronize clocks is at the level of 2 to 4 seconds, it's actually a constant. The temperature doesn't kick in faster than that time frame. So we synchronize every 2 seconds. And you have to keep on doing this, forever, basically. So what are the 3 steps to find this middle red line? First is support vector machine. That's the ML technique from recent times. Coded probes is a way of knowing if a packet is a lucky packet or not, without even looking at historical data. I send a packet, I want to know, was this guy lucky or not lucky, to use the language that Ella introduced. And then third is this idea of network effect, which as soon as you see it, it'll be clear what it is. So first, let's do support vector machines. This is the same picture as I had before. And if I use what I call soft margin support vector machine, basically they're a technique for classifying labeled points. So I want to draw a line or a hyperplane in general that separates the blue points from the green points and gives me like sort of the middle line. And because there's no way you can draw a middle line when there are blue points and green points mixing up like this, you use what are called soft margin support vector machines, and which kind of ignore small outliers, but you can see that they're affected by the outliers, so you don't get an exact margin. They're already off, but nevertheless, already this red line, which is not correct, will give you a sync of between 300 to 400 nanoseconds accuracy, okay, for that data. Now we have these noisy timestamps, and we'd like to find a way to get these lucky packets as I like the language, so I'm going to keep using it. Okay. So how to identify these packets that are lucky, zero queuing delays or no timestamp noise? So instead of thinking of one packet, think of it as two packets. Okay, so a probe is now two packets, not one. And on the sender side, you sent the first packet and the second, and they went into the network. And let's say the separation as measured at the sender's clock is about 10 is equal to 10 microseconds. Okay, it could be whatever it is. You don't have to shoot for 10 microseconds. It could be 6. It could be 60 microseconds. It's some number. Just record what it is. Okay. And as you go through the network, three things can happen. One is they come out on the other side separated by a lot, more than 10 microseconds. In this case, no matter what happened to the first packet, the second one was not lucky. It got delayed. Therefore, it was separated by more than the initial value. We'll reject those. If the opposite happens, the first packet got delayed. You'll reject those. And we'll only keep the guys that are nearly equal to 10 microseconds on the receiving side. And the reason for this is most likely there was no queuing delay, that this pair of packets both were lucky. It'd be very difficult for a network to arrange for them to emerge on the other side with exactly the same separation. And so they actually both must have got through without delay. Okay, so that's who we'll keep. Now, if we take this noisy data and apply the filter and get rid of all the guys who failed that test that I showed you in the previous slide, you see here all that's left is most of the lucky packets are left in place, and most of the other guys are kicked out. And some do make it. Like if you look at this closely, there are all these pairs of points. This pair got through. There's a pair of guys that got through. So it's not impossible, but it's very unlikely, that the network will give the same exact delays. Okay, does that make sense? So this is an automatic way of detecting whether a packet or a probe was lucky or not. Okay, and this is very useful if you think of the wireless context where you could have a node that is moving. The minimum delay is not a quantity you can count on anymore, because what do you do when A is stationary and B is moving? But if you have this sort of lucky packet concept and use coded probes, you can detect it. So this will improve by a factor of about 4 on the previous, this red line is worse than this red line by a factor of 4 in terms of accuracy. Finally, final step is this network effect. So historically, people have looked at synchronizing clocks, pair of clocks at a time. So if you want to synchronize 50 clocks, you do reference and the first one, then the first and the second and third, like that. Instead, we're looking at a mesh, so we can actually look at triplets of clocks, or quadruplets of clocks simultaneously. So let's say there are two clocks A and B, and exchanging probes, and all the support vector machines, they worked out what is the offset. And then there's a third guy called C, who's also exchanging probes independently with A and B. Okay. So now A says, if my clock is at 10, B must be at 10:15. A and B both agree that that is the case. And then B and C have been exchanging probes, and B says, okay, if I'm at 10:15, C must be at 10:05. And C says that if I'm at 10:05, then A must be at 9:50. By the way, pairs of clocks all agree to this. But of course, if you go through the loop, you detect that there's an error because it's not adding up to 0. Okay, it's not up to 0, but it's not. This is allowing us to detect that there's an error just to begin with. You can use this sort of thing for any algorithm. You could use it for NTP, you could use it for PTP, you could use it for anything. Okay, so to know whether it's doing the right thing or not. Okay, if you go around a circle and they don't agree, then there's a problem. So now the question is, how do you correct it? Like this, or what is the correction? which way do you apply it, okay? Luckily for us, because we have lots and lots of loops coming from the probe mesh, we can use more information, and there's basically like a maximum likelihood estimate we take, and then that allows us to come up with corrections on the edges, individual edges, and so this is showing you the effect of it. On the x-axis here is this value k. K is how many other nodes a clock is probing, how many other clocks a clock is probing. So if you're only probing 2 guys, then your probe mesh has small number of edges, so you get a small number of loops. As you go higher, you're probing more, you get more edges, more loops. So your error should go down because you have more and more comparisons you can make. As you go down this path, as you go up this x-axis from 2 to 12 in this figure, the mean error will go down, but the 99th percentile error will go down by a lot more. So it really is hard for clocks to be outliers. You've been compared against so many other clocks, and then so you will end up getting, you will be detected if you're off. Okay, so that's the main third idea. Any questions on this? These are the main 3 ideas. There are a few details that are in the paper. You can take a look. But this is how we know.
So far, there are no questions in the chat box. Feel free to add your questions. If you have a question now, please speak up.
Professor Balaji, this is Otan again. I don't understand something. I mean, first of all, the idea is noble. It's pretty obvious that it's a noble algorithm, and it gives I assume we can extract great accuracy if we are using hardware timestamp. But I don't understand how the system gave up reliability so fast. I mean, treating time as a software computed is something that seems so weird to me. As you know, the highest priority event in an operation system is the tick, and this is because the entire reliability of the scheduler depends on time. And ignoring a physical element like a physical oscillator that can be disciplined with the PLL seems like, I don't know, it seems weird. Can you put some few words on that?
Yeah, I mean, the physical oscillator can only simply control and discipline the clock, right? It is not going to do anything more. It needs some way of knowing which way to control the clock. That's all it does. Okay. It's not going to be any better or worse than your ability to detect whether you're off from the reference clock by some amount or not. And so all it does is help you get, the control part, all it does is help you get, alignment with the reference. And so if you want to eventually control the clock, that's what you'll do. And that's what we in fact do, okay? You have to control the clock, and you have to know how to control it. But the software solution tells you at scale whether, given one reference clock and some like 50 or 100 or 5,000 follower clocks, whether each of those follower clocks is actually tracking the reference clock correctly or not. And now correctly is down to like, you want to be as accurate as possible, right? And so that's what this algorithm is doing.
This is all written in software, correct?
Yes.
And so you've got these delta times in these hard boundaries of like no buffering, this lucky one, as you call it. But surely, so I can understand that through the packets making their way through the network and they get lucky and they arrive. But the software itself, depending on the priority of the processor, what the core is up to, you dedicating a core that does nothing but sniff these packets
No. The timestamps. So keep in mind there are two points here. Okay. The software is only used for processing, okay, but the data is taken at the NICs, and that's a hardware timestamp at the moment, okay. You can go from Okay,
Right.
so at the transmit time, you take a timestamp, and the receive time, receiving NIC, you take a timestamp. So let's stay with NICs for a second, and I'll go to the host also in a sec, in just a second. Okay. So right now, think of it as that's the data that is taken in hardware, and the processing is done in software.
Okay. Okay. So
Every
you're getting the
second.
calculation, but so really you're talking about the clocks at the NIC cards is what the synchronization is happening.
Right. That's for now. I'm going to leave that behind and go into VMs in my demo and say how that works also. Okay.
Okay.
There are
So,
other questions. Sorry, please speak up.
Yeah.
I have another question. So every node speaks with its immediate neighbors, or with all the nodes in the network?
No, you don't have any immediate neighbors. There are two just servers connected. This is the key difference between the hardware approach and the software approach. The hardware approach, you need to know that I'm connected to that switch, and then that guy's talking to that guy, and so on. So there's no immediate neighbor notion here. There are servers in a data center, and servers can talk to each other, and they send probes directly to each other.
So each server, how many probes it sends? To 1, to 10, to 1,000?
Every 2 seconds, a node sends 100 probes. So it's the data, what I showed you here, is representative of what happens. But in the initial work, we were probing at a higher frequency than is necessary. So the demo I'll show you in the cloud is 100 probes every 2 seconds.
So another side note. Obviously, the financial traders, you've got a GPS clock input to some network cards where you get a global timestamp done hardware. I mean, what you're talking is very clever and very sophisticated, but what's wrong with the keep it simple, stupid? Let's just bring a global clock in around the world, an atomic clock, and synchronize to that.
Yeah, it doesn't scale so well. I've not heard of a single PTP deployment more than 250 or 300 nodes. If you know one, I'd like to hear about it. I'd like to talk to someone deploying that. It's not that easy.
Why couldn't it be? I mean, if we suddenly said let's build all computers that they have a global reference clock coming in, an atomic clock timestamp, and they synchronize their clocks to all of that, wouldn't that be a lot simpler way to do it? I mean, obviously it's an industry mandate, and so yours is clearly a lot easier to do, but it just feels like it just feels almost too smart. Keep it simple, stupid, or the simplest solution is the best solution.
It's most expensive though. It's just think of what you're proposing, right? If you look at a rubidium clock, okay, that has a certain rate at which it's going to change. And if you just look at a rubidium clock, it's probably going to be the same cost as a server. So you're just doubling the cost of your site, the network, just to put the clocks in. And you have to still synchronize those clocks even though less frequently. You'll eventually have to synchronize them, right? So it's not like
yeah, I don't understand how the GPS timestamp. I thought the GPS was pretty accurate, but maybe I'm wrong.
Not necessarily, by the way, because so just something, we've been working with the financial guys for a few years now. There are just effects like this. You probably all know this, but I'm just going to remind ourselves this. The time at the bottom of a tall building and the time at the top of a tall building are not the same, okay, just because of gravity effects. So the time at the top of the table I'm sitting at and the time at the bottom are not the same, up to 10 to the minus 18 in that range, okay. Not enough to make any material difference to current applications, but if you now look at the height of a building, it begins to matter, okay. And so if you really want to be accurate, and you really then have to just not only measure the wire precisely that you get from the GPS super precisely, because every meter is 5 nanoseconds, okay, speed of light on wire. Now you have to
4.9.
Sorry?
4.9.
4.9 what?
Then it's 4.9 per meter.
4.9 nanoseconds per meter.
Yes.
Well, 5 is a good rounding number. Okay, so
Yeah.
let's just say yes. Okay, so
We try to be accurate. Yeah, I'm just funny. I'm sorry.
it's fine. The refractive index of glass matters, whatever it is, you can just use that. Only in speed of light and vacuum we know exactly what it is. Otherwise, the material matters. Okay, so let's say so you have to measure that exactly, and then you bring it in, and then folks have these multi-terminal repeaters. Okay, so I've seen this box. It's about the size of if you open a MacBook Pro, the bigger one. That's the size of it. Okay, and it has 36 terminals. That size box. All it does is take that single GPS pulse that comes from the top and repeats it. So now you have 36 servers to whom you're directly connecting this, because you don't want any hops. Then if you have hops, now you have to deal with the rest of the lucky packet problems. Okay, and so you pretty much build a second network to synchronize the clocks of the first network that you're interested in. And many financial companies actually do that. There is a management network on which the load is light, and they use that to synchronize clocks because they can't afford to have the probe packets going in the same path as their payload. And you might think that that's because they care more about time and the probe packets may get delayed and the accuracy of time gets hurt. That's true. But they actually care more about the payload packets because that's their order that they don't want delayed behind the probe packet. So just the serialization delay on the wire that a probe packet might take is not something the financial guys are willing to put up with in some cases. So you're now looking at this scenario where in small setups, you can do this. And there are very good PTK-enabled switches that can actually give you very accurate clock sync. They also use 4 gigahertz clocks. So now you can get to 250 picoseconds kind of, clock periods compared to, let's say, your typical 8 nanoseconds or 6 nanoseconds periods that you get if you had a 125 megahertz clock or something in that range. Okay, so people have thought about these things pretty carefully. The real enemy is not so much congestion. That is an enemy. Okay, it's not so much that. If you could synchronize clocks and not have to worry about them for an hour at least, then life would be great. But unfortunately, temperature effects kick in and vibration effects kick in. So if you just replace all your clocks with temperature controlled crystal oscillators or vibration resistant, that alone, okay, that's not even an atomic clock. That is going to boost your cost by too much. And so, this is really the rub of the whole thing is that it's a cost versus scalability sort of trade-off. And so the solution we're proposing is actually, if you look at this sort of loop effect, it's not unnecessarily clever. It's actually necessarily clever. I don't know why people didn't consider asking 3 clocks, are you all in agreement? Okay. Because if A is synchronized to B and B is synchronized to C, then C must be synchronized to A. Failing that, you already know there's an error. Okay. So just doing open loop and never checking, I don't know why we haven't done it as a community. Okay. So in that sense, the necessary check is what you would do. It's like parity checks, right? So some of the ideas are, available in other areas. We're just bringing it in here because it's necessary.
I must say that it seems that if all this great idea was one layer on top of PTP, like implemented as a profile, or as 2 collateral PTP layers that one is synchronizing between them, I think you get an applause wall to wall here, because you get all the benefits from both systems. Indeed, you manage to reduce the cost, but it seems that there is a vulnerability issue when the network scheme is changing. If I'm a data center guy, I would be terrified. What happens if I now connect new nodes? The entire algorithm is modified. What happens if there is a storm in the network?
No, wait. Can you just slow down, because you're making assertions. Why don't I show a demo of what happens when nodes come in and go? Okay, it's rather trivial actually. It's less complicated than might appear. And the point about PTP, there's nothing stopping, but a clock can only be controlled by one algorithm at a time. Okay, you can't control the clock with PTP simultaneously along with NTP simultaneously along with us. That doesn't work. Okay, because they're just trying to do move things, one way and the other. So you have to allow the clock to be only control the one algorithm. And, we can assist PTP and tell how PTP is off, and it can take that hint and change it if it wants. But the problem is the big difference you have to keep in mind is PTP requires the network to be synchronized. We're simply saying, I have 100 nodes in a cloud. I don't want to synchronize the entire cloud's worth of nodes. I don't even know who those nodes are. I only care about my 100 nodes, my 100 VMs, my 100 servers. Why do I have to synchronize the whole data center?
Well, one thing I want to add, maybe there is a misalignment how we are basically defining, let's say, PTP or something. Let's start from scratch. Let's say where your algorithm needs, let's say, the coding between the two packets of 10 microseconds. So that on its own, you probably will have a better. You first let's go like right from the beginning. You agree that if you have better mechanisms to basically run the data that you're feeding your SVM, you will have better performance. We agree on that, right?
Yeah, but I think that, yes, I agree with that. But
So
the thing is, I don't
stationarity.
need, no, hold on. I don't need the two packets to be separated by 10 microseconds. As I said, I'm not shooting for it.
You're
It's
not,
whatever it is.
but you want it stationary. You want them to be as accurate as possible because you want that value.
No,
Because
I don't understand. I don't understand what that means. What does stationary mean?
it means like whatever number you choose, you want that number to really be there. You don't want another variance to kick in because your entire algorithm relies on that. Let's say
No,
I
it
choose,
doesn't.
let's say 10 microseconds, but then in reality, I end up with like 11, 12, 9, and then
That's
every time
okay.
I change
That's
the
okay.
station.
No, that's okay. So, Alma, just to make 100% clear, this first probe pair can go 10 microseconds. Next one can go 6.7. Third one can go 7.3. I don't really care. Whatever the number is, I just need to be recorded. And I just want to compare it at the receiving end. Okay.
Sure. So when
That's it.
you want to record it, again, you want to know what you're sending, and you want to see exactly what you're getting in the back. So
Correct.
all of these things can really benefit hardware timestamping.
But I'm using hardware timestamps right now.
So then that's the thing. Here the nomenclature is basically when we say PTP, we assume hardware timestamping and transparent clocks. I honestly don't see anything going wrong with basically applying whatever like all your algorithm is bringing up on this on the infrastructure that PTP has. And by combining PTP, what Dotan is saying, he's not saying like, oh, run, let's say, the PTP servo while you're running your thing on the same clock while you're running NTP. No, we're just saying the infrastructure that PTP has, which is hardware timestamping, and let's say how the grandmaster works and how the transparent clocks are there, that can easily solve this problem. As a matter of fact, the way that we are looking at like how we can scale the data set in a data center scale, PTP, we're not looking for synchronize the entire network. Therefore, we're not even looking for boundary clocks. We're saying simply just transparent clocks. And again, you can handle the package to where you are going just with a basically unicast structure. So now if we have everything, hardware timestamping and transparent clocks, and we feed it to your SVM, we really will get a great results because now, and that's where he was saying that this can be simply just a profile, and the profile is basically
No,
this is
guys, I don't understand. No, I don't understand what you're proposing. Okay. I'm allowed to have my algorithm. You're allowed to have your algorithm. Okay. I was hoping to present my algorithm and tell you what the consequences are, because those consequences are independent of whether it's PTP or whatever. Okay. And then that would be the talk. But I'm happy to take this discussion on because it seems that there is sort of there's a versus thing going on here, and I don't know what that is. Meaning, you can use these techniques in NTP can use it. It's nothing exclusive to anything, right? It's just an idea. You can use coded probes in PTP if you want. Nobody's going to stop that. Okay, it just happens that we've used it. You can use network effect. You can use it. But eventually, I'm saying something that is, I don't need the switches to cooperate. It is irrelevant to me the switches cooperate. That's a statement. Now you're saying, well, switches cooperate, can you see an improvement? Of course I can. If the switches cooperate, what will happen is if the switches can place timestamps, then I get extra information and extra loops. And that to me is important. Okay, that is, we could use that. So I know how, there's a coexistence possible, but not because you can do it this way or that, but rather you can actually do something bigger, not just there's another way of doing the same thing. Okay, so if you give me switch timestamps, what will happen is instead of just having loops at the edge, I can have loops in the middle, and that gives me way more information to get corrections. Okay, but that's a different idea. It's an idea that is different from saying I can use network effect for NTP. Yeah, of course you can use it, and I'm saying it myself. Okay, so there are some generic ideas, and then there are some new ideas. That's what I'm saying. So there's no versus here. It's mostly PTP is doing something, we're doing something else. But I'm saying something important, which I think is that do you want, if you have to synchronize 100 nodes across the network, you need to synchronize the network. That's worth asking. Okay.
So what do you mean by synchronizing network? That's like
The switch, the first hop switch. So there's a node A is the reference. Then the switch connected to node A needs to understand and forward. It needs to synchronize with it, or it needs to be transparent, meaning exactly measure the delay and forward that delay for the probe packet.
So we're talking about like transparent clocks, not boundary clocks.
Transparent clocks still need to send the duration. How long did the packet spend?
Like
right.
the residence time, yeah.
So you need to understand. So there are switches that need to understand the protocol, or switches that don't need to understand the protocol at all, and treat the probe packet just as any other packet. Okay. So I'm asking that question: whether are you happy to just let the probe packet be treated like any other packet, dropped, queued, whatever happens? Okay. And I'm saying.
Of course, it's great if I don't need transparent clocks, let's say when I go between data centers, because I don't have control over there, like when I go to WAN.
But also, what are you gaining by doing it is the question, right?
Yeah.
So can I get to the next few slides, because I'm going to say
Sure.
Our algorithm just beats PTP in accuracy. Would that be enough to say it could be considered? It's not our opinion, by the way. Other people have tested it. We haven't directly had access to a PTP testbed, like at Stanford or elsewhere. So Deutsche Börse. So I think this was what happens at load, and so here are test beds. I think I should share my screen again, or can you see my screen?
Let's share it again.
How do I do that?
Just press that one. Yeah. Full screen it.
Okay, can you see it?
No, it's your video.
Okay, now I can. Okay, so
yes.
So as I said, the work started with the Google's Jupyter testbed, and we built our own at Stanford. But neither of these, we had comparison to PTP. Deutsche Börse did it, and in 2018 announced it. In their testbed, PTP came at 50 to 60 nanoseconds on the same workload that Huygens came in at 5. Okay, and Facebook did their own test. And on the saturation load, this is not until you saturate it that you get PTP's 8 microseconds and Huygens is 140 nanoseconds. Okay, so this is, again, I'm just saying these numbers, and I was not going to spend time on this slide, so I can go on to further things. So there's something to consider here is a way of concluding this segment of the presentation. Is that okay?
Just one comment. The telecom industry has spent, I don't know, maybe 10 years working on a lot of these type of techniques, let's say based on, lucky packets, or what they call, packets that traverse the network with the minimum floor delay. They came up with various metrics like called the FPP, or floor packet percentage. But they were never able to put a hard requirement that says, for a given network topology with these kind of links in them, whether they were microwave links, GPON links, DSL links, capable of putting some hard numbers into the accuracies or the precision that you could get out of these techniques. Because there was always conditions where the floor of the network would change. And that imposed a lot of additional constraints on how you design these algorithms, on the oscillators that you want to use. What do you think is different here in the data centers and what you have seen working in the data center?
So I think the first point I was making is that there's an automatic flow detector with these coded probes, right? That the fact that I don't need to historically look at data to find out whether this guy was lucky or not. And of course, it's not guaranteed, because you see some unlucky packets, namely guys got delayed, do make it out to the end with the same exact separation. So it's not a foolproof way of detecting lucky packets, okay? But you do have a method just in and of itself. And then the second thing is simply that, even at high load, that's one of the things I wanted to say, is that if you're synchronizing with respect to 5 other clocks or 10 other clocks, at a given load, my path to, let's say, 3 of these 10 guys is congested because I'm at high load, but the path to 7 other guys is pretty good. So I'm going to sync with those guys, okay? So you get this redundancy built in when you sync across using a mesh and not a tree. In a tree, you only have one neighbor above you. And in a PTP setting, for example, is a tree, and then I'm synchronizing one guy above me, and then I'm synchronizing one guy below me. I mean, one at a time. I could have multiple children, but I'm talking about one at a time, okay? So from the point of view of who's my source of time, if I have multiple, then it's great, because now, it's like a peer-to-peer system versus, people have used phrases like wisdom of the crowds and whatever. It's something similar here, that if they're all mutually synchronized, then if 3 of them are unavailable, the other 7 will keep you going until those 3 come back, and then some of these guys will go back. That's what's happening.
So on that note, I have a question on, is there any way to trace your clock, your synchronization to the golden standard? Say you have one clock that's connected to the GNSS in the network. You want it to be the golden standard. How can you make sure that the entire group does not drift away together?
Great question. The answer is yes, you can. It's a really good question, because, what if everybody's lying, okay? But so long as you have one guy who's the source, it can tell, because the final step is actually not taken by the local clocks. The local clocks only run the support vector machines and give you the local offsets, okay? The global calculation is done by that reference or the coordinator, okay? And so that's the step at which you can detect it. And so in the interest of time, let me not say more about it, because I realize there's literally only 5 minutes left. I haven't shown the demo even, let alone tell you about consequences. So I hope that's a good enough answer for now, but it's a good question. Okay.
Sure, thanks.
So let me show you what happens if you were to do this without hardware support at all. Okay. So here is a data center. So you can go to Google Cloud. So this is TikTok is a startup of which I'm a co-founder. It's come out of the work we've done, and it's available for you to play with on Google Cloud or AWS or Azure or even multi-cloud. Some nodes in one, some in the other. I've just launched on Google Cloud 50 nodes in the West Coast region, and the nodes are all free running. That is, nobody's controlling their clocks right now. So these are the 50 VMs. Okay, this green guy in the middle is the reference. So it's an arbitrarily chosen node. It's not like it's tethered to anything. So it could be drifting, but right now its offset is 0 with respect to itself. This red node is one of the remaining 49 VMs who is actually running ahead. So this red node is 33 milliseconds ahead of the green node, and this blue node is 481 milliseconds behind. So blues are behind and reds are ahead. Okay, and the way we know that this is true is because every node is talking to 5 other nodes in this probe mesh. So this pink node is talking, and then here we have this pink node is talking to 5 others, including the reference. The reference node is not distinguished in any way in this probe mesh, okay? And so they all make these local calculations and stuff, and eventually the coordinator works out every 2 seconds what is the offset of every clock with respect to the reference clock. And the vector of offsets is taken, and this is the median, and this is the 90th percentile, okay? So now I can change this from what we call observation mode. So nobody's controlling the clocks, and we could have had NTP control or TT, Huygens control. So let me now turn on control, which means these clocks are going to get skewed, or slewed, I should say, sorry, slewed towards the reference. And the first step could be a big step because 926 milliseconds is a long way to bring to zero or towards zero. So after that it's going to slew. Okay, so just the control has just taken over. Okay, it takes a few seconds, so you can actually follow it here. So the clocks were drifting. I applied the control. It took a few seconds for the control to kick in, and now the control is going ahead. So again, this is the median, the green, and the orange is the 90th percentile. Okay, so you see it's getting closer and closer to zero, but it'll stop at about hundreds of nanoseconds. Okay, that's the best. This is almost the best we can do. Okay, this will come down a little bit more. There's an outlier somewhere there. Okay, so while that's happening, someone was asking about nodes arriving and leaving. So let me just kill a bunch of nodes. So I'm just randomly killing 12 nodes. Okay, so what will happen is nothing. I mean, those nodes will be dead. Those VMs will decommission. And you can see the effect on clock sync accuracy is not going to be significant. So these 12 nodes died. So it got worse because nodes are gone. And now new neighbors will be found. And then it'll sync back again, without much of a hiccup. And so this is what happens when nodes die. Let me give it a little bit more time. This node is still 9 microseconds away. He's going to come in. And so, again, you can follow that here to see how bad it was. So I have to zoom in, I guess. So here's where the clock syncs were going on, and I killed a bunch of nodes, and it got worse, and then it's getting better. Okay, and so it's back in the few hundreds of nanoseconds. So I can bring them back in. I don't have to bring them all back in. Let me bring some of them back in. And this happens in networks. Nodes leave and come back. I think I brought 6 back in. Okay, so now again, what will happen is the new nodes will be just get integrated. They'll start probing. The coordinator will know that they've arrived. So you see these nodes were the ones that were drifting. Now they've been assigned new neighbors. So they'll take a few seconds to get slewed back in. Okay, so that's what happens. And so this is sort of pretty straightforward in that sense. You don't have to it's I think it explains itself. So that's what happens with clocks and no load. Okay, so you can pick an edge like this one, and we can look at the one-way delay. So you can see that the probes are minimum delay, median, 90th percentile, and a no load. And I can apply some load. Like I applied 55% load. Our instances on Google Cloud are throttled to 2 gig. We have cheaper instances. So I applied 1.1 gig of file transfer type load. And I'm going to keep that edge constant so you can see what happens when the load kicks in. So I had no load up to here, and suddenly I have load, and so you can see the one-way delay shoot up. So this is what I meant by it's a direct way of measuring network load, path load, point A to point B. And this is something applications can just directly use now, and I don't have to build a management plane for the network and stuff. So my area is networks. I've worked a lot on network measurement and worked on like building counter arrays and stuff in switches. If you don't have access to them, this is a straightforward way of doing it end to end. Okay, so this is what happens in a single data center, and the point here is there is no NIC timestamps; it's virtual machine timestamps. Okay, so the variable stack latencies do play a role. I think someone was asking this question before, but the cloud operators have got fairly fast path from the wire through the NIC into the VM. Okay. So that it's a fairly good network. So this is a single data center. Now, if you look at what happens across long distances, I've got 50 nodes on 3 data centers across the US, and they're already synchronized. So I'm not, they're already synchronized according to the Huygens algorithm, and you can see the accuracy here. It'll change. Because of multi-protocol label switching. So the path, suddenly you see, so the reference node is in the central zone. These clocks are going to be typically better synchronized than those guys and those. And what affects performance here is long distance link quality. And that is captured here. So for example, let me pick that alert. And that alert says that there is a link that underwent a sudden change in its one-way, so if I put my glasses on, this is 37 milliseconds, close to, and down to 34. So a 3 millisecond drop for a while and then back up, okay? And this is just purely multi-protocol label switching. So you've gone from some one wavelength on the fiber, long distance fiber, to different wavelength, and that does affect clock sync quality, by about a few microseconds around that point in time, okay? And you can see there are many of these going on. In the last 1 hour, when I just started these instances before, the talk, and you can see there are several of them going on. Here's another one, okay? So you can see these sort of roughly 2 to 3 millisecond. In this case, it's 3 millisecond again, okay, change. And there's one more going on right now. So what happens is that you're roughly around single-digit microsecond at long distance, better if you don't have path changes because of NPLS. So those are sort of the main things with the demo. And let me, so one last thing to show you is if I look at this probe mesh, some of these guys are probing locally, and each node is probing locally and also remotely, but certainly not probing everybody. So if I want to add an edge between that pink guy and this one, so I can monitor delays, it's as easy as just picking, like in PowerPoint, just adding an edge. Okay. And now once the edge is added, probes will be sent down that edge, and you can monitor the delays. So for example, like that, for whatever reason, you're interested in monitoring the delays, I just added that edge, and you can start monitoring the delays. Okay, so this is really how this works. That's the demo. I don't know how I'm doing on time. What's left is just, the use cases. What is the use of this? Why did we do clock sync, and what are we doing with it? It may be useful to tell, but I don't know where we are in time.
Let's go a little bit further. Like because we're gonna have it recorded. If someone wants to drop, they can drop. We're gonna have the recorded session anyway.
Okay. Thank you, Ahmad. Thank you. So let me I'm not going to spend too much time on this network visibility. I just finished talking about it. I showed it to you. So basically, the use case one is you need a management plane conventionally. So normally you need a management plane to. Okay, you have. Sorry, the animation just takes out the management plane quickly. I'm sorry about that. Okay, so you need a management plane so you can query the boxes, but this is sort of a more of an edge-based way of understanding network delays. Okay. Second use case is on-ramp, which is sort of I worked on congestion control for many years, and you can sort of think of designing a new version of like a TCP algorithm or a layer 2 algorithm. Like QCN is an algorithm that I developed for IEEE standardization more than 10 years ago, along with others. It takes a lot of effort, and many of them are doing really well. Any changes are really, at the level of making more network support come in and inform more congestion information. So we flipped it around and said, can we just look at a simple method that, like on-ramp on the highway? If the highway is congested and I can measure it, then I will stop the cars from entering the highway. That's it. Okay. Simple in that sense. So what a source can do is if the source and receiver have synchronized clocks, then for packets that are transmitted, so the source is sending black, green, blue packets. It is now about to transmit the red packet. It has to decide, is the network congested? If so, I'll hold back the red and subsequent packets. Or is it not congested, in which case I will transmit it. And the information it uses to make that decision is the last packet that was acknowledged, the most recent ACK, right? That packet has the latest information on network congestion. So if this one-way delay is bigger than some threshold T, then you say network is congested, and then you pause. And you pause until, one-way delay minus threshold. So meaning, let's say one-way delay measured is 100 microseconds, and the threshold is 50 microseconds. Then you pause for 50 microseconds, 100 minus 50. The threshold is 50, and then you measure 69 microseconds. Then you pause for 19 microseconds. That's the algorithm, okay? So it really is like a priority flow control that Ethernet uses at layer 2. You can move it to the edge of the network and just use one-way delay as the measurement to trigger pause. And you don't change the congestion control algorithm on top. Just let it be whatever it is, okay? Whether it's cubic or BBR, whatever it is. It can be whatever it is, okay? So you can now run this on both on-prem and in the cloud. And so the paper is coming out in a month and a half or so in the conference, NSDI. If you want a copy of it, let me know and I'll happily send it to you. So this is cubic on Google Cloud. There's a foreground traffic, which is an application traffic. We're interested in the request completion times. This is the mean 90th percentile and 99th percentile, etc. They all improve the moment you just use pause at the edge or on ramp. Okay. You also improve the background traffic, which is causing congestion. In this case, it's like a web search traffic that we used at 40% load. And we changed the algorithm in the second case. This is BBR, which you will know as another algorithm that Google has proposed recently. And here also you can get strong improvements just by pausing at the edge. And so with our collaborators at Facebook, well, we ran this for in their setup because their storage traffic can hurt compute application latency because it can overwhelm storage traffic can overwhelm links and switch buffers and can cause severe packet drops for compute applications. So the question is, can on-ramp help to throttle the storage traffic using exactly one-way delay measurement? And so we're comparing cubic with cubic and on-ramp at one pause threshold, at a smaller pause threshold, versus DC TCP, data center TCP. This you may know is an algorithm at least 10 years old. I'm one of the co-authors of that paper as well. So it uses switch signals to no congestion, but we don't have to do that here. So compute latency improves dramatically, but roughly a factor of 10 if you just use on-ramp and pause on the edge. This doesn't also hurt storage throughput. You can see the scale is compressed, so it's almost the same throughput that you get whether you use cubic or on-ramp. And finally, the reason for this improvement is here. If you look at packet drops in a 5-minute run, cubic drops like 173 million packets. Okay, this number is 173 million. And cubic plus on-ramp, this is down in the 130 something, okay? And DCTCP is about 2000 something. So there's a huge, huge difference in the number of packet drops. And that's just because the storage guys just overwhelm the bandwidth. Okay. So this is a second application. And finally, I'm not going to spend too much time on this. We've spent a whole quarter at Stanford last fall building and using a financial exchange in the cloud for teaching and research. And this is very interesting because many of the financial exchanges are considering moving the exchange into the cloud. And the number one thing that they need to make that happen is what's called fair access. So you have to give your market participants all fair access, which means it's like one of these game engine things, guys. If you are here and you submit your order, then the time taken for your order to go from gateway to matching engine must be essentially the same as for another participant to go from a different gateway to the matching engine. Otherwise, it is unfairness. They may go ahead of you. And so it's basically you want to enforce a global FIFO. And you can do that with accurate clocks. So I've defined what fairness is. I'm going to leave it in the interest of it getting recorded, but not spend time on it. But you can use synchronized clocks and resequencing buffers to get fairness on the inbound side, and on the outbound side, you can do something else called hold and release buffer. in the interest of time, let me stop there. And I thank you for your patient listening, as well as all the questions, by the way. I'm happy to take on more questions if you have them.
Sure. Thank you, Professor Balaji. It was a great presentation for sure. So we have like a bunch of questions here. Like again, one is from Dotan. He's asking, how do we measure accuracy actually?
So in the case where you have test beds of the PTP type already, those folks, like, the Deutsche Börse folks measured it on their setup. Same with Facebook. But when we do it, the way I show you is this network effect. And if we compare ourselves to what is measured by instruments, how accurate is it? It's pretty accurate. I can quantify it if you want. So that's one way. The network effect not only tells you that there's a discrepancy, it even tells you how much is the discrepancy.
Yeah. So the other question is from Lassie Jensen. Is the overall offset number an average or it's an RMS?
The overall offset number is a number, statistically, the ones I reported to you, the means and high percentiles, you have both. So it's a random number, and so it has its distributional characteristics.
And then another question from WatchTech, I think it's a follow-up kind of from Dotan, is he's asking, how is the synchronization quality measured? Is that with a physical signal like PPS or the offset self-reported by the node?
So for the paper, we built an FPGA-based way of doing it, okay, at Stanford, because we didn't have, and that's pretty accurate. We've explained how it works. You can take a look, and I can explain it. Okay. For what you saw in the cloud, because obviously no one's sitting there measuring anything, it's through this network effect, like I said. And if you compare how accurately network effect will predict or estimate the error, it's pretty spot on, and I can tell you more about it if you're interested. But those who run the tests, some financial institutions that I haven't named, but I've also done the test, have got spectroscopes and stuff, and they can do it with that, and they've done it. There are PPS is one way that I know the Facebook friends have done it with. So it's there are multiple ways of testing, and pretty much somebody or the other has tested it in all those ways. We just are not the people who have access to PPS or PTP setup. The spectroscope's also super expensive. In fact, so expensive that some firms don't buy them. The way some London exchange financial person told me, well, not the exchange, but a financial person told me was, it's £250,000 is how he said it. So we rent it. Okay.
So anyone else from the audience has a question, please unmute yourself. Okay, I think then there is no more question. Yeah, okay, thank you very much, Professor Balaji, and we'll have this presentation recorded and available on the website.
Yeah, so just if I may just make one closing.
Yeah,
First of all, thank you again. But I found this very, very interesting forum to present in, because you guys are both savvy and interested. That is actually what I was hoping would come out of this talk. Okay, I came prepared to say a few things, and I was hoping to make sure I got that out. But at the same time, happy to spend more hours, discussing details. And I do think that, I've already talked to Ahmed and mentioned that there is an interesting way in which, for large-scale deployments, you probably want something like a spine layer where PTP is syncing spine-level switches, and then you can use that to feed off of to the leaves using a software approach, because you want something that what I call temporal inertia, that is an inertia built in time to prevent nodes from leaving actual time. It's easy for one node to deviate from actual time. It's not easy for 10 nodes to deviate from actual time together. And that's what I mean by temporal inertia. Okay.
Yeah, definitely. Like we're looking for a hybrid solution where we can benefit from all these things all together. And I think that would be fantastic. That's why I think it's good to really embrace all these things all together.
Sounds great.
One other question: Do you see this? I guess there was a bit of overhead there. Do you see this sort of making it set its way into the firmware in RTL of like the NIC cards and then driving the system clock of the motherboards, or
Right,
something?
right. I actually think that this is ideal almost from a smart NIC type implementation perspective, because the NIC timestamps are great to have, first of all, because as people already observed, it avoids having the stack latencies, right? That's number one. Number two, increasingly smart NICs all have P4 or they have DPUs, they have so many different kinds of processors. Many of them are almost ideal for doing things like support vector machines or just cleaning up data that using more recent ML techniques, right? And that combination is just almost just too good to pass up on. Okay.
No. So all right, that's encouraging. I guess you can also build it into FPGAs quite easily in the firmware. So
I agree. FPGA guys have got very good at things like matrix multiplication and stuff. So one version of support vector machines can be done with that. It just really comes down to how noisy is your data. Some of the telco folks can dedicate, because it's things to circuit switch by nature. They can actually dedicate a lucky packet doesn't have to be lucky. It's just an everyday packet because there's just a dedicated circuit.
I guess in your applications, where you're saying by backing off, you're getting rid of these latency, the noisiness issue. But one thing is, if the whole system was designed, we live in this virtual world of where it's really anarchy in terms of synchronization. In this, you've got layers and layers of software that seem to be doing that. One company that I'm from the UK and I'm Bristol, so I've got an affiliation to them, is GraphCore. I'm not sure if you've looked closely at GraphCore, but they work on a bulk synchronous parallel execution where they compute and then they move data. So you have a very deterministic system, and they have hardware synchronization from in their IPU boxes. They have a dedicated synchronization link. Now, not quite. I'm sure it's not locked like yours is in that sense, but everyone's going to this common heartbeat, and they communicate and then they communicate and process. So they're going back to first principles and saying, a bit like a lot of high performance computers, you need to work in a very synchronized way so the machine works in harmony and doesn't thrash itself to death. And so it's interesting that this is the reason because I think there are some paradigm shifts our industry needs. We need a Tesla event, and I think that synchronization is one key aspect of our industry needs to learn about synchronization across these many.
So I agree. I mean, if I may take one minute to respond, because I think it's an important point. See, when we were doing self-programming networks, we thought that we would go down that sort of automating, which is a theme that many different areas are looking at. But as soon as the clock sync thing happened, and we realized that this is more foundational for distributed systems, we sort of put the brakes a little bit on the automating part, and then took more of the time synchronization thing up. And now what I can say is the first decade of this century, the success was all about, the virtualization, everything becoming VMs and cloud and big data and all that coming up. And the decade that just passed is all about both big data and AI/ML type of techniques, moving big time into the cloud. But it's all about looking at data and batch processing, the paradigm. Right, looking at bulk data, and you're looking at yesterday's business receipts or operational data, and then you're trying to get insights out of it.
Yeah.
But as more of the real world is moving into the cloud, like autonomous vehicles controlled from the cloud, or financial industry, moving into the cloud, decision making will come into the cloud with deadlines.
Yes, absolutely.
So the next gen is really, the next gen is really all about like deadlines. So I feel like this decade that will have there'll be a strong theme around timeliness, let's say.
That's where I came from back in the 80s. We had parallel computers to test weapon systems, so we fired live missiles against simulated targets, and you had a closed loop. You had a Mach 2 missile that you had a closed loop around, and so the time synchronization of your compute was critical. And so it just feels like that world, that parallel world is coming back in a heterogeneous way, and synchronization just seems to be whether it's synchronization at a coarse grain, like back then it was a video frame rate, or a bit like GraphCore doing it. They're doing it literally at a time step level, compute, then transmit the data, and they synchronize at a very, very low level there. So I think this is a critical aspect of computing going forward. So that's great. Thank you for your contribution. I enjoyed it.
Okay, wonderful. So
I have a question, Ahmed.
Go ahead, Hasham.
Given what Professor Balaji presented, which obviously the scheme he developed in Stanford is more accurate than BTP or NTP, how we plan to use it in our project? How we plan to use this scheme in our data center project?
I think, like, if I can elaborate, like, I think you mean like how can we scale up this implementation in a data center, right?
How we can, because Balaji scheme is different from BTP, which what we are trying to do now. But I'm saying if
we
you
still
would like,
have a reference clock and we have the nodes that they need to synchronize. So
we synchronize them using this messaging scheme that he developed. How we can use that instead of using BTP? We don't have to use BTP. We don't have to use BTP if we use this scheme. If my understanding is correct, we can use BTP, or we can use what Balaji presented.
One thing I may add here, there is a confusion. There's a confusion that is going on. Like, let's say, I'll say, like, from our end, when we call PTP, unfortunately, when we call PTP the hardware timestamping, the transparent clock, boundary clock, all the infrastructure, exactly. and the PTP servo, like basically that is running the PTP algorithm. So with and that is really creating a lot of confusion, I'll say, from our end. While when you look at, like, basically what Professor Balaji has, from my understanding, please feel free to interject me, Professor, if I say something wrong. I feel like whatever is presented, Huygens, is capable to do things without the hardware timestamping, of course, but obviously there's always like you can have better performance if you have the data with less noise, if the data is more consistent. So that's why if you move to, let's say, hardware timestamping and have like all these infrastructure that PTP needs, and you run, let's say, Huygens, you'll get all the robustness, while really you don't change that much in the hardware. The hardware is always there, and you can switch back and forth. But if something works better, why not, right? So that is what I see overall, what is going on here. And
so my understanding, Ahmed, is that we can run PTP with the master selection algorithm and boundary clocks or transparent clocks. That is one protocol and one scheme. We can even not even use that scheme altogether. We don't need all this best matching clock.
Grandmaster, because you need the source of time. You're right. You don't need, let's say, the transparent clocks. You don't need the boundary clocks. But again, from what I see even here, and I think everyone agrees, like, if you have transparent clocks, then you will definitely have more benefits. Then you get your, like, quote unquote, your lucky packets more often. So then you can have, like, again, more accuracy.
Just a couple of things. I have a hard stop at 12:30, unfortunately, but I think there's two senses in which both of you are correct in that PTP, as described by 1588, is a protocol that has been specified so vendors can build to a common framework. That's what Hesham is saying, but I think what Ahmed is saying is think of PTP's ideas and capabilities and not the defined way of doing things. And both have both of these points of view that are not conflicting in my view. Okay. We could use more information. Obviously, it's always everything's going to help. There's just no question about it. For the software version, by the way, we don't use coded probes because they're not as effective, it turns out, because the spacing is not. But we still get hundreds of nanoseconds of accuracy. So if you look at it two different ways, what we have learned is this. There is an industry like the financial industry and the trading side of the financial industry that does care about clock sync down in the nanoseconds. But almost every other industry doesn't care about it at that level of precision. So in other words, it is sufficient to be sub-microsecond, and it doesn't have to be, any other thing, distributed databases, any other thing, okay? Any AI, ML, anything large scale doesn't seem to, if you look at large scale Spark jobs and stuff, none of them requires super accurate. Like microsecond already is too good, actually.
Yeah.
Okay. So the question is really, PTP can go all the way to the nanoseconds, but if you're willing to settle for something like microsecond or two, PTP may be more effort than required, and NTP is not good enough yet. Okay, so you get this sort of chasm. There, something like the software-based approach may be useful. But on the other hand, if you really want to think of data center-wide accurate clock dispersion or time dispersion, then I do think that, I've spoken to, like folks like Ahmed and others at large scale, hyperscalers, that it is worthwhile to consider a spine level where it is PTP, and so things don't change that much, and because you guys have nicely defined hierarchies, and so now you don't have to worry about every switch, every port, every server. So you have some of these that are, holding time in this inertia sense, and then you can distribute from that spine more easily using a software-based approach, because you can have nodes going, and like especially in virtualized environments. Okay, so this is definitely worth a conversation. I'm happy to talk about it. Okay. So with that, again, let me thank everybody, and especially Ahmed and Hesham and others who sent the invitation out. You know where to reach me. I'm at Stanford, Balaji Stanford or edu. Looking forward to more conversation.
And we'll have the link and everything like on the website. So as Professor said, you can reach out to him. Thank you very much, Professor Balaji.
Thank you.
And yeah, thank you, everyone.
Thank you very much, Professor.
Thank you. Bye.
Bye.
Thank you. Bye.